Hello everyone, I'm Alex, and welcome back to the AI Research Roundup. Today is May 5th, 2025. We're diving into an interesting ICLR conference paper published just over 3 months ago on January 22nd, titled Energy-Based Backdoor Defense Against Federated Graph Learning. This paper tackles tricky backdoor attacks in Federated Graph Learning, that's FGL, where graph neural networks, or GNNs, are trained collaboratively. It proposes a method called FedTGE using topological energy to detect malicious clients. Alright, so this diagram really lays out the difficulty. You see how the attack triggers themselves can have diverse structures and get injected in various spots, making them hard to pin down? Compounding this, the federated nature means clients inherently have different graph structures and node features. This combined diversity and heterogeneity really complicates filtering out malicious updates, often tripping up traditional defense methods. Okay, so building on those challenges, this figure shows the architecture of their proposed solution, FedTGE. You can see the two main parts. At the client level, they use this, quote, energy-oriented training to make models sensitive to malicious samples, generating distinct energy distributions. Then, at the server level, these distributions are clustered to identify and filter out suspicious clients before propagating energy similarity to refine the final aggregated model. It's a neat two-pronged approach. Okay, moving to the results. This table really puts FedTGE to the test against other existing defense methods. It shows performance across 5 different datasets under both IID and non-IID conditions. We're looking at node classification accuracy, that's A, and backdoor failure rate R. Well, FedTGE, highlighted in bold, consistently achieves the best results, especially on that combined metric V, showing its clear advantage in defending against these attacks. Following up on those strong results, this figure digs a bit deeper with an ablation analysis. It explores how performance changes when you tweak key parameters, like the number of energy epochs for client training, and that similarity threshold tau used for filtering. You can see the impact on accuracy A and failure rate R across different datasets and conditions. Well, these plots help fine-tune the approach and confirm that these energy-related components are indeed crucial. Right, and this figure really visualizes why those energy components are so effective. It shows the energy distributions for normal and malicious clients across different trigger types. Look, at the start, energy epoch 0, the distributions overlap quite a bit. But after 10 epochs of energy-oriented training, see how the malicious client's energy distributions, shown in red and purple, become much more distinct from the normal green ones? This separation is key for the clustering detection. Building on that separation, this figure gives us a PCA view of the client energy distributions on the PubMed and CS datasets. You can see the different clients plotted based on their energy characteristics. Well, the red circles appear to highlight the clusters identified as malicious by the Finch clustering. It really demonstrates visually how this energy-based approach successfully groups and isolates the bad actors, which is key for effective filtering. Alright, putting it all together. We've seen how FedTGE cleverly leverages topological energy. First, it distinguishes malicious clients using energy distributions and clustering, then refines the aggregation based on energy similarity. Well, it really provides a solid defense against backdoor attacks in federated graph learning, especially tackling data heterogeneity without needing extra validation data. Thanks for tuning in to the AI Research Roundup. I'm Alex. See you next time.